Welcome back to the lead channel on another episode of looking at kinematics of vector addition. Today we're going to look at vector addition using components, because if we take two vectors, for example, in example 1, if we have someone who's walking 4 meters at an angle, changing direction to 12 meters in another direction. If I draw this one out, it kind of looks like this. 4 meters at 35 degrees north of west. That kind of looks like this. 35 degrees north of the west. That would be this angle over here. And then followed by 12 meters at 50 degrees north of east in the other direction. But this time, this is 50 degrees north of east. Now you have two vectors. When you add them together, they cannot form. They or may not form a right triangle. In that case, what do we do? Well, last class you looked at how to break down your vectors into their components. So today we're going to look at how do you add vectors by adding up their components. We are going to look at what we call the component method of adding vectors. No matter how many vectors you add, 2, 3, 4, 5, or 6, you will always be able to use the component method and it will always work. To calculate what we call the resultant vector, the resultant vector is when you add up more than one vector together, and the resultant vector is the arrow, the vector from the initial point to the final point, and the shortest path in between. This is what we call the resultant vector. In the question before, the resultant vector would be the final displacement. If you had added Leo's two displacements together, that would be his resultant vector. Below, I have a list of what you can use to follow to calculate the resultant vector using the component method. But before you even do anything, I would recommend start out with a compass. Draw out your compass. So I'm going to label north like this, east like this, and because when we talk about vectors, the direction matter, I'm going to label which directions are positive, which ones are negative. For north, I'm going to make north positive in the positive direction, east in the positive direction, horizontally, north positive direction vertically. Therefore, south will be negative and west will be in the negative direction horizontally. Okay, I want to label that first. Now I'm going to draw the vector. To draw the vector, I'm going to do a better job than what I did over here. So let's start with Leo walking 4 meters at 35 degrees north of west. So let's draw this first. Here we have the first one, and now I'm going to draw the second one, which is his second displacement, which I'm actually going to label red this time. And this is going to be at 12 meters, 50 degrees north of east. This is 12 meters. Maybe a little bit more. There you go. This is 12 meters at 50 degrees north of east. And if you don't remember the nomenclature of the vectors, please refer back to the previous video for a catch-up. Okay, so now we've done the first step, which is drawing out the vectors. This is to get us an idea of what it looks like. As a result, we do know that if we look at the resultant vector or total displacement from initial to final positions, this will be the shortest path between the two. And I'm going to call this the resultant vector, RT, in this case. Now, if you know the cosine law, which I'm not going to cover in this video, you can use the cosine law to find the remaining side of your irregular triangle. But if you haven't, that's fine. Also, you can't use the cosine law for more complex examples involving multiple vector addition problems. But the component method, again, will always work. Okay, so number 2, we're going to break the vectors down into their horizontal and vertical components. Sometimes it may not be necessary, but in this case it seems like it is. Starting with our first one, I'm actually going to label each vector individually. The 4 meters, I'm going to label this as S1 with a little hat on top looking like a vector. And then S2 will be this guy, the second displacement over here. When I break these vectors into their components, I'm going to start with my S1, displacement number 1. And if it first goes west, I'm going to call this S1X. And then the S1 now, then it goes north. And I'm going to call this S1Y with a little hat. Okay, I'm not going to calculate anything. I'm just going to draw everything out first. And notice that for green, I'm labeling my horizontal components with green and my vertical components with purple. With my second vector, S2, I have my X component, which I'm going to call S2X, and my Y component here, S2Y. Here I have broken down my 2 vectors into their components. Now I can calculate them out. So let's do that one first. So let's start with my X components. So we're going to calculate components. Starting with my X components, I have S1X, starting with this guy. And if we take a look at our little right triangle, we see that S1X is adjacent to the 35-degree angle, which means I'm going to use cosine 35 in this case. So I have cosine 35. This is equal to my adjacent, which is my S1X, over my hypotenuse, which is 4 meters. Before I calculate this out, this one, if I solve for S1X, this gives me, if I multiply both sides by the 4 meters, I get 4 meters times cosine of 35. And solving it gives me 3.276 ... meters. And in this case, the S1 is going towards the west. So I'm going to write the direction, but I also could use the negative and positive signs to indicate direction as well. So this can be 3.276 west, or it can be negative 3.276 ... meters. And I'm going to save this on my graphing calculator as the letter A, so I can recall it later. That's my S1X. Now for my second X component, S2X, and if I go to my right triangle, if I take a look at what's happening here, relative to my 50 degrees, my S2 is also adjacent to my angle, which again means I am going to use cosine again. Ooh, how convenient. This is never going to happen twice in a row. Or it could, but be careful if it doesn't. So as cosine 50, this is my adjacent, S2X, over my hypotenuse, which is the 12 meters. If I solve this out, this gives me, multiplying both sides by 12, I get 2x. S2x is equal to 12 meters times cosine of 50. And solving this on my calculator, I get 7.713 meters. And this is towards the east this time. And because it's east, and if I designated east to be my positive direction, I can leave this as east, or as positive 7.713. And on my graphing calculator, I'm going to store this as B so I don't forget the values. So these are my X components. Now for my Y components. I'm going to start with S1Y. Starting with S1Y. If I take a look at my triangle, this is 35 degrees, and my S1Y is the opposite side to my 35 degrees, which means when I write my SOHCAHTOA, I'm going to use sine this time. Sine of 35, this is equal to my opposite, is S1Y, over hypotenuse, the 4 meters. Solving this one out for S1Y, I get S1Y is equal to 4 times sine of 35. And the graphing calculator looks like this. 2.2943. 2.2943. And if you take a look at the map or my drawing, both the y components, the vertical components are in the north direction. So I'm just going to label this with north. And that should be it. I can leave it as positive and it should be fine. Okay, then I'm going to go ahead and find the components for fs to y. And going back to my triangle, this is my opposite side relative to 50 degrees, which means I'm using sine again. Sine of 50 equals to s2y over 12 meters. Solving for s2y, I get 12 times sine of 50, and on my graphing calculator, oops, I should have said the previous one, I'm going to save that as c. There you go. Okay, and the new one, 12 times sine of 50, and that's 9.19. 9.19 ... meters, and this gives me it in north. I will also save this as a letter D, so I can use that again. Okay, so here it is. These are all my individual components, and as a result, we have done bullet point number 2. So that's vertical, and the green is a horizontal.